Okay, so the last law we'll take a look at in terms of gases is actually probably one of the easier gas laws, and that's the Dalton's law of partial pressures. And this takes into account when we're dealing with gas mixtures. Remember, gas mixtures, we can often refer to those as solutions, right? And these are very common. You look at mixtures of gases compared to just pure gases, individual gases. In other words, we encounter gas mixtures very often, as opposed to just individual gas samples. So the idea behind this is that if you have a mixture of gases in a container, each gas is going to behave as though it occupies that container alone. And as a result of this, it will exert pressure called its partial pressure. We can actually calculate this using the ideal gas equation. So for example, you have 1 mole of a gas like nitrogen in a 5-liter container. At 0 degrees Celsius, we can use PV equals nRT, solve for the pressure here of, in this case, of the N2. That'll be equal to N times R times T over V. So we substitute our moles, our gas constant, times the temperature divided by the volume, and we see that it's 4.48 atmospheres. If we add to that container a mole of oxygen, a different gas, for instance, well, the container has the same volume, right, which is 5 liters. We have the same number of moles. We're using the same gas constant. We have the same temperature, same volume. So the pressure of the O2 is also going to be 4.48 atmospheres. So the total pressure then is simply the sum of those partial pressures of the mixture of gases, right? So the total pressure, just adding together the partial pressures of the whatever gases that are there. In this case, we have 2 different gases. You could have 6, 7, 15 gases, doesn't matter. Just add those together and we get the total pressure of the gas mixture. So in essence, if you can add things together, you can do Dalton's law of partial pressure, right? So the way that it's stated officially is that the total pressure exerted by a gas mixture is simply the sum of the partial pressures by each component in that mixture. So we have our notation, so the pressure here is equal to, that's a symbol sigma, that means the sum of, and then PI would be the partial pressures. Each gas in that mixture. Right, and we can use the ideal gas equation to solve for the partial pressures of each gas if we wanted to. So when we have our gas mixtures, in addition to applying Dalton's law of partial pressure, we can also now come up with a term that allows us to specify the relative amounts of the components in the gas mixture by using what's known as the mole fraction. The mole fraction, it can be applied to lots of instances, but we see it a lot in gases. And the mole fraction of something is exactly what it sounds like. It's the mole fraction for substance I, whatever I is simply the number of moles of I that we have divided by the total number of moles that we have in that entire sample, right? And the symbol for mole fraction here, this funny looking X that you see. The subscript I would be the mole fraction of I. Okay. So mole fraction of I would be the number of moles of I, whatever I is, divided by the total number of moles. Yeah, and it's a fraction, so you will get a number less than 1 always. When you add together all of the mole fractions of all of the components of a sample, you should get 1 because it should add up to the whole thing. And because they're fractions, they don't have any dimensions, there are no units, it's just a number that we're going to find. So what we find is that for gases the number of moles and the pressure are proportional to each other at specified temperature and volume. So what we can say then is, in addition to the mole fraction being equal to the number of moles of I over the N total, we can also say that the mole fraction of I is, we get the same number if you divide the pressure of I by the total pressure in that sample. And if you rearrange our equations, right, we can actually solve for both the mole fraction, or the number of moles, and also the pressure of each of these things by doing a simple manipulation. So if I move the total pressure to the other side, what I get is the mole fraction times the total number of moles would give me the mole fraction, I'm sorry, the number of moles of I. And if I rearrange this equation in a similar way, right, what I get is now, if I multiply the total pressure by the mole fraction of I, I get the pressure of I. Okay, so these are going to be two important relationships that we can use. We have a mixture of gases in our sample. So let's take a look at an example where we can apply this relationship. So it says FDA approved the use of nitric oxide, NO, or nitrogen monoxide to treat lung disease. And it comes in a mixture in the form of a nitrogen and nitric oxide mixture. So it says calculate. So again, when you read these equations, there are certain things you can look for that tell you, or that would imply or suggest that there are certain gas laws that we're going to use. So if you see mixture in there, right away you're thinking, well, is there a gas law that deals with gas mixtures? The answer is yes. Probably going to use either Dalton's law, or maybe the mole fraction relationship. That's what we're thinking once we see some of these clues in the problem. So let's calculate the mole fraction. There we go. Calculate the mole fraction of NO. So that's what we need to find. We need the mole fraction of nitrogen monoxide, nitric oxide, and then we're given the volume of our cylinder. The volume of this entire thing is 10.00 liters. And then we're given a temperature at 25 degrees Celsius. We convert it to Kelvin right away, so that's 298 Kelvin. And then we're also told, okay, we have a gas mixture here. We have nitrogen, we have NO in it. We're also told that this mixture contains 6.022 moles of N2. And the total pressure is 14.75 atmospheres. So pressure total here is 14.75. And what we need is the mole fraction of NO. So what is the mole fraction? Well, the mole fraction NO is simply the number of moles of NO. So N NO divided by the total number of moles. Okay. So we have the number of moles of nitrogen, N2. What we need, we would still need the number of moles of NO. And then once we get that, then we can do the division or the relationship. So that's what we want to get to. We can use all the other information to get to that point. So what we can do then, right, is we can find the total, because we're given the total pressure of this thing. We can find the total number of moles, so N total, by using the ideal gas equation, PV equals nRT. And we can solve it for N. And to rearrange our equation, we get N is equal to PV over RT. Okay, so our pressure, total pressure there is 14.75 atmospheres. Remember now that total pressure is due to the combined pressure of the NO and the N2. Our volume of our container is 10.00 liters. our gas constant, 0.0821 liter atmosphere per mole Kelvin. And then we have our temperature, that's 298. Kelvin goes away, liters go away, atmosphere goes away. So you have moles in the denominator, and it's 1 over moles in the denominator. So 1 over 1 over mole will give us mole. And then we just use put our calculator to use. We end up with 6.029. That's our N total. Okay, to get the mole fraction, bring this back down here. So we have the mole fraction of NO would be the moles of NO over the total moles. Okay, we just found what the total number of moles is. Okay, we still need the number of moles of NO. Well, guess what? We were given what the moles of the other component was, the N2 was up here, it was 6.022. So you can get the number of moles of the NO would be N total. Total number of moles minus the number of moles of N2. So we have 6.029 minus 6.022. So that would give 6.007 moles, probably the number of moles of NO. Then we substitute this stuff into an equation. So the mole fraction of nitric oxide would be 0.007 moles over the total moles, 6.029. Moles cancel out. We get a dimensionless value, so that's 0.001. That's a 1/1000th of the sample is actually the nitric oxide.